I'm here with a Kioxia CD8. Not just one CD8, 24 CD8s. And the only platform that can really take advantage of that many CD8s are brand new ones. Genoa. Even Sapphire Rapids. What? It's just U.2. You can use it on any modern server. Well, 24 of them is going to saturate memory bandwidth unless you've got a lot of memory bandwidth, which is going to be DDR5. It's a whole different ball game than what we've seen up till now. Let's do a deeper dive. Our story actually starts 5 years ago with the launch of AMD EPYC. And this is how far we've come. You might remember this chassis. It's our Gigabyte 2U Naples platform. Yeah, EPYC Naples, first generation, 16 cores per socket, the frequency optimized parts. Still rocking out in this configuration. This is the clock optimized EPYC CPUs that came out later. So there's 16 really fast cores per socket, 2 sockets in here. And this chassis was originally rocking 24 of these 4 terabyte Intel P4500s. This is the same exact configuration that I helped Linus with, Linus Tech Tips. This thing's been on 24/7 since then. Gigabyte reliability, And what we ran into was, when these things are firing on all cylinders, it's saturating main memory bandwidth. Even though we've got 2 sockets with 8 memory channels of bandwidth each, there's not a lot of room left over once you get the data copied to memory. PCIe is basically dumping data into memory as fast as possible, and you don't really have a lot of overhead to do anything else. In our case, we were running ZFS, and ZFS makes internal copies of the data, so it'll copy something from one place in memory to another place. That also uses memory bandwidth, and that created a little bit of a problem for us in that we weren't using the system as optimally as we could because of the extra copies, and because we were using most of our memory bandwidth, it meant that the I/O devices were staying idle at least some of the time, because the system was really busy with just memory copies. But oh, how far we've come. This other smaller EPYC system, this is the 75F3. This is also 32 cores, but in a single socket and with 8 memory channels. And the DDR4 3200 interface of this could easily run circles around our Naples configuration. That's just 2 generations later. And now we're on Genoa with 12 DDR5 memory channels. It's a whole different ball game. We've got all the memory bandwidth we need, and then some. Of course, the NVMe storage devices like our CD8 have moved on as well, and 6-8 gigabytes per second, they're twice as fast per drive as our P4500s, so that's also a whole different ball game. I love the smell of cores in the morning. That's right. When you've got 24 drives, even the old P4500, you could saturate main memory bandwidth. Even though we've got 2 sockets and 16 DDR4 memory channels, when each drive is saturating the PCIe 3, not 4 bus, there's not really a lot of leftover bandwidth once you're reading from the SSDs. Do you read it and send it back out over the network? You enter this world of things like direct memory access, DMA, and it gets complicated in terms of how things are implemented. You have hardware acceleration and offloading and things like that to try to speed these things up. When we're talking about PCI Express 5 and DDR5 and the new geometry of these servers, the server class CPUs, whether you're talking Team Blue or Team Red, either one, it's a whole different world. Just basic testing, just run the 8-64 memory benchmark, which is not perfect. 768 gigabytes per second with 12 DDR5 memory channels on our AMD Genoa platform. That's almost a terabyte per second. 3/4 of a terabyte per second. Okay, if you do the math, the DDR5, there's some cache stuff happening there. It's not quite that fast, but it's really darn fast. Even if our PCIe 4 Kioxia SSDs could saturate the 4 PCIe lanes that they've been given each, and all 24 of them in our Genoa chassis, as a percentage, we're not going to use anywhere near as much memory bandwidth as we were on the older platform, to say nothing of more recent platforms like, DDR4 3200, it's clocked higher than our older DDR4 platform if we're talking about EPYC Milan, or we're talking about 6 memory channels on Skylake Xeons. But it's still, as a percentage, those older platforms are losing a ton of their connectivity just because there's not enough main memory bandwidth with DDR4. DDR5 is that much of a game changer, to say nothing of PCIe 5. We don't even have drives that can saturate PCIe 5 yet. Enter Kioxia CD8, brand new SSD. I get the first look at the CD8. Standalone testing, that's easy. A single CD8 looks almost pedestrian, but by enterprise standards, it's top-tier NAND flash technology. With more than 8 queues going at the same time, you can achieve almost 1 million IOPS per second. The single sequential transfer rate, over 6 gigabytes per second, almost 7 gigabytes per second. A little better than Kioxia's rating for this SSD, but we're definitely pushing the bandwidth limits of PCI Express 4. Even at just 6 gigabytes per second, times 24 drives in a server chassis, that's pushing 144 gigabytes per second. That's a real challenge to the main memory bus when you think about it that way. I mean, even though on the Genoa platform we've got 12 memory channels, and Sapphire Rapids we have 8 DDR5 memory channels, 144 gigabytes per second is a significant percentage of that. In fact, it's almost all of the available bandwidth that we have on the system just to transfer from storage, to say nothing of sending it back out over the wire again. Some world records you can achieve with just the burst speed of the drive. Some world records require endurance, and the CD8 drives are about endurance and sustained performance. You see, consumer drives, yeah, it's like 6-7 gigabytes per second, but as the drive fills up, and as you're asking it to do more than a few hundred gigabytes at a time, the speed falls off dramatically. It's not really the case with the CD8. 15 terabytes for a single M.2, filling it up all the way with 12 terabytes of space, the performance remains pretty consistent and pretty high. It's hard to achieve that with NAND level storage, but this kind of performance is the norm and the expectation in enterprise drives. Now, to be clear, the CD8 is a production enterprise class drive. If you look at the specs on paper and you're used to seeing the specs for consumer drives, it looks like it doesn't stack up. If you look at the Samsung 990 Pro, for example, we're talking about 7,800 megabytes per second and the write speed, and it's fabulous. The problem is that Samsung 990 will fall apart under load. You get past 50 gigabytes, 100 gigabytes, 200 gigabytes for a write operation, and the speed of that drive tanks. You are going to start out, sure, at 7,800 megabytes per second, but by the time you've done 100, 200 gigabytes of writes in a very short period of time, your write speed is going to be more like 500 megabytes per second, barely faster than SATA speeds. Not only that, while that's going on, the number of IOPS that drive can sustain goes way down, and that's because of the nature of triple level and even quad level cells. Quad level is going to be a little bit worse. The drive is juggling a lot of things in the background. Its read speed can be kind of okay when we're talking about triple and quadruple level cells, but when you have a flash memory cell that stores 4 bits of information, if you only ask it to store 1 bit, the thing that reads the state of the cell can read very quickly. It only has to figure out, is this a 1 or a 0? But if that cell is actually storing 4 discrete states, meaning that the drive is actually a little bit more full, this is kind of a performance hack that consumer drives have, then that thing that figures out which level the cell is at, because it could be one of 16 levels with 4 bits stored in this thing, it has to do a 16-level phase discrimination in order to figure out the state of the 4 bits in that cell. And guess what? That's orders of magnitude slower. So when you're juggling reads with 4 bits per cell as opposed to 1 bits per cell, that's going to slow down. And when you're juggling writes, where the drive is already got some information on it, or the single level cell buffer, as it is sometimes called, your write performance is also going to tank. Enterprise drives cannot do this. This is the reason that flash drives took so long to be adopted in the enterprise. Everybody was rocking the OCZ 128 gig drive, which, by the way, does anybody even still have one of those that works? They all died. Why didn't the enterprise adopt them? Because they all died. And it's kind of like that with consumer drives as well. That Samsung 990 with the firmware updates, that ain't going to fly in the enterprise. The CD8 does not have those issues. And if you look at the performance, it's like, well, but the performance isn't, it's consistent. It's consistent. And so for an enterprise class drive, when you look at those performance numbers. This is class-leading performance for a commodity enterprise drive. And a commodity enterprise drive, it sounds like that would have a negative connotation. But when you're buying a server, you want to buy 24 drives, and you want to have specific performance characteristics. And actually, Kioxia subdivides their CD8 performance into, sort of more read-heavy workloads and then read and write-heavy workloads. So you can buy a drive specifically tailored to whatever it is that you're going to run. Because gone are the days of using these kind of SSDs as a read cache or as a write cache for mechanical spinning rust and all the other stuff. Which, by the way, mechanical spinning rust, very predictable storage, even though it's a very low number of IOPS and very low, just not ideal in a lot of ways. It is very predictable. It's a known quantity in terms of reliability and how slow it is. But it's not really the case with Flash. Sometimes when you read something from Flash, it can take a few dozens of milliseconds, and sometimes it can take microseconds, depending on how fast it is and a whole bunch of other parameters that are going on with that. And so that's why it's so important and also kind of exciting that the innovation is happening in a different way when we talk about enterprise drive. When we talk about generalized performance, we can run the performance numbers. We can run the performance numbers with 800 gigabytes of test file size and see the FIO output and to see the performance geometry of one of these drives that is under an extreme amount of IO pressure and IO stress. And with this performance and these numbers, it actually performs really well in that context for FIO. Does it perform well enough to break some world records? Well, I enlisted the help of Glenn Berry, Microsoft MVP and Microsoft SQL Server aficionado, because these drives can help me, I think, answer a question. You see, we've got Sapphire Rapids, AVX 512, high performance, and our Supermicro Big Twin case. We've also got the AMD Genoa Titanite system. We've got a lot of NVMe drives. Microsoft SQL Server supports something called Quick Assist, and in the Skylake days, Intel offered a Quick Assist PCIe card. This is a PCIe accelerator. So we were kind of in this confluence of AMD with their Genoa CPUs adding AVX 512 support. And then we've got tried and true AVX 512 support on Intel Sapphire Rapids, but also Intel's adding AMX, and they're also adding optional accelerators to their Sapphire Rapids platform. Well, I just so happen to have Sapphire Rapids in the form of our Supermicro Big Twin server. It's actually 4 sockets in this thing, 2 nodes, and that's going to run Microsoft SQL Server really, really fast. Our other system, our AMD Titanite system, is the best of the best from AMD. But we're actually going to put 2 32-core, the F-series CPUs in our AMD platform. 64 cores in this chassis, 12 DDR5 memory channels per socket, and we're going to outfit it with 24 of our NVMe drives. And we're going to see if we can break a few world records. What are we going for? The fastest SQL server in the West. Now that's actually not going to be in this video, because as I've been working on this video, ran into a few problems. One of them is the chassis that I have for Genoa is configured for 16 NVMe, not 24. I need more cables, and you need to use less PCIe connectivity between the sockets whenever you're going to do that. So you can actually have 160 PCIe lanes on that platform. It's also a little bit of a challenge to get that many NVMe drives on our Supermicro Big Twin system with the Sapphire Rapids system. That's 12 NVMe per node. Okay, 12 times about 6 gigabytes per second. It's going to be nowhere near main memory bandwidth, even with the 8 DDR5 memory channels of the Sapphire Rapids platform on the Intel side. We're going to need just a little bit more bandwidth than that in order to eke this thing out. The question on my mind was basically, I've got the Intel PCI accelerator, the Quick Assist card that I borrowed from Glenn Berry. And this was all the rage in the Skylake days because it'll accelerate backups, it'll accelerate decompression. It's an accelerator exactly the kind that Intel is selling us in Sapphire Rapids, except integrated into the CPU in Sapphire Rapids as opposed to PCI Express. The question on my mind is, does the AVX 512 afford better acceleration than last gen's PCI Express acceleration? This is going to maybe give us a portent of the future to see how things are going to go for accelerators on the Sapphire Rapids platform, especially things that are getting built into the CPU. And this is also maybe a little bit of a mystery. It's like, okay, if Intel is facing some real competition and some real challenge in terms of raw compute and just basic things like AVX 512, do we see a future where the Sapphire Rapids platform wins with the extra cost accelerators? Like, does AMX do it? Does AVX 512 do it? Where does that break down? And in order to figure that out, I need insanely fast storage. And so Kioxia was kind enough to let me borrow enough 15 terabyte CD8 drives in order to be able to do that test from an enterprise level. And this may still not be fast enough. I may have to resort to cheating and using consumer grade drives, which you would never use in the enterprise, but just because they've got the burst speed. So I want to see the next generation of enterprise drives, maybe how fast those go, to see if I can break a few world records and sort of put that together. These are our two test platforms. AMD's Genoa with the Titanite platform rocking, yes, just any one of these CD8. Literally all across the front. And our Sapphire Rapids system only has 12 NVMe because this is a 2U 2-node system, the big twin from Supermicro. And this is our Quick Assist Accelerator PCIe card, but more about that in a second. Goes in there. We have to connect all these PCIe lanes for all these devices, and we're short 32 lanes, 2 X16 slots. Fortunately, our Titanite platform gives us that. See these bridge cables here? They connect the two CPUs together. So if you need a really quick path between CPUs and banks of memory, you've got it. But if you'd rather have lots of PCIe connectivity, you can disconnect those and connect them to more PCI Express devices. That type of configurable PCIe is unusual in a normal server chassis. The integrator, like Supermicro, would choose this chassis is going to have more PCIe connectivity, or this chassis is going to have more inter-socket communication at board design time. So it's a little unusual situation with our AMD Titanite platform for the Genoa SP5 CPU socket. Why isn't it working? Ugh. So the problem that we ran into is one of signal integrity. In order to go from 16 to 24 NVMe, I need cables to connect to the motherboard and run up front. This one's a little too short. It's not really what it's meant for, and the connectors aren't quite exactly what I need. And the lead time for these cables is about 6 weeks, give or take. I gotta return my drives before I can really finish this project. I really think we can break a world record here, but we get close. But we still learn some important things. I'm also adding a new chassis configuration for Sapphire Rapids, one with more NVMe slots. One with more NVMe slots and U.2 connections, or U.3. It's a fake! Because it can't do PCIe 4 signaling speeds. My shipment was intersected by Center Serverina. Alright, so I wasn't able to break the world record, but we did learn a lot of really interesting stuff, and I'm going to give this another go. I'm going to do another run at this. I want to see I want to see one of these platforms do SQL Server operations faster than the fastest system in Azure. I think we can do it. I think we can do it, level 1. I think we can do it. But we did learn some really interesting stuff. First, the PCIe accelerator, completely obsolete by both Genoa's AVX 512 as well as everything in Sapphire Rapids. Oh boy, those CPUs are fast. PCIe accelerators don't make any sense. I see why Intel has not updated their PCIe accelerators, even for the, sort of, let's call them entry-level Xeons, because people aren't buying 96-core SQL Server licenses. They're unaffordable. Nobody can afford to buy them. It's literally $500,000 for a 64-core CPU SQL Server, enterprise license. But high clock speed, 32 cores or maybe dual 32 cores. Okay, maybe at like the highest end, certainly what the highest end Azure systems are. But you don't need an accelerator, at least a PCIe accelerator, to get the job done. And it's a really close race between our Sapphire Rapids system and our dual 40 core versus our dual 32 core system from AMD. It's really, really close. I'm gonna have to get some more help from Glenn Berry. Look for a blog post from him. Definitely check out his channel and, you know, subscribe over there. We're gonna do some more tests and some more exciting things, but I gotta spend some more money on hardware and get some cables and do some fun, exciting things. So, Supermicro Big Twin, unconstrained performance, AMD Genoa. Also unconstrained performance, but different. It's exciting times. I'm Wendell, Level 1. I'm signing out. This has been a first look at the Kioxia CD8 and the performance in sort of real-world-ish enterprise scenarios. I'm signing out, and you can find me in the Level 1 forums.